In this video, we will see design of axial loaded short column. The data given are axial load on column represented by P, which is 1500 kN, and width of the column is given 250 mm, and effective length of a column is given 3 meter. M20 grade of concrete is using, so FCK is 20 Newton per mm square. Fe415 grade of steel is using, so Fy which is equals to 415 Newton per mm square. Step 1 is to find the cross-sectional dimension of a column. Before that, we will find whether the given column is short column or long column by using a slenderness ratio. The slenderness ratio is calculated by using these formulas: LEX by D and LEY by B. If this ratio is less than or equals to 12, then it is considered as a short column. If it is greater than 12, then it is considered as a long column. Here length of the column is given as 3 meters, so 3000, and B we know width of the column is 250, they are given. If we substitute this value, we will get slenderness ratio as 12. Hence the column is designed as a short column. Next, let us provide the depth of the column D, which is equals to 2 times the width of the column. So 2 into 250. Then depth of the column we will get it as 500. Therefore the size of column, which is equals to 250 mm width by 500 mm depth. After finding the cross-sectional dimension of a column, the next step is to check for minimum eccentricity. About a major parallel axis B, which is equals to 250 mm. If we consider this is a rectangular column, along the shorter side we will get a maximum moment of inertia. So this axis, if we draw here the x-axis, then the axis along the shorter side is considered as a major axis. So dimension along the major axis parallel, which is equals to 250 mm. Then lateral dimension is 500 mm. Then E minimum eccentricity, which is calculated by using this formula, that is unsupported length of column by 500 plus lateral dimension by 30. Here unsupported length of column is 3 meter given, so 3000 by 500 plus lateral dimension. Here it is 500 divided by 30. Then we will get 22.67 as a minimum eccentricity. And this is a condition we have to find. E minimum, that is minimum eccentricity, should be less than 0.05 times the lateral dimension. Here lateral dimension is 500. If we substitute, then E minimum we will get it as 25 mm. We got E minimum by using this formula as 22.67, which is less than the E minimum by using this condition. Therefore, the column is designed as short axially loaded column without any moment. If minimum eccentricity value exceeds this value, then we have to design a short column with a moment by using that eccentricity value. After checking of eccentricity, next is load calculation, that is load coming in a column. Axial load on column, which is given as 1500 kN, which is a working load. The ultimate load will get by multiplying 1.5 to working load. Then the ultimate load on column we will get it as 2250 kN. After that, next step is to find the area of steel requirement. To find the area of steel required, we will use this formula, which is given in IS 456 class 39.3. Here PU, which is equals to 0.4 FCK AC plus 0.67 FY ASC. PU is axial load on the column. FCK is characteristic compressive strength of a concrete. AC is area of concrete. Fy is characteristic strength of a steel, and ASC is area of longitudinal reinforcement. We have to find this ASC area. Here AC we don't know, area of concrete. So area of concrete, which is equals to total area minus of area of steel, then we will get area of concrete. Here total area is width into depth of the column minus of the steel. Then we will get area of concrete, AC. By substituting all the values, then area of steel we will get it as 4628.77 mm square. For this area we will provide the reinforcement. Let us assume 28 mm diameter bars. Then area of 28 mm diameter bar we will get it as 615.75 mm square. Next, number of bars we will get it by area of steel, the total area of steel, divided by area of single 28 mm diameter bar. Then we will get 8 number of bars required. Therefore, we are providing 8 number of 28 mm diameter bars. So, area of steel provided, we will get it as 4926.01 mm square. After providing the area of steel, the next step is to design of lateral ties. Let us assume we are providing 8 mm diameter bars. Then the pitch or the spacing of the bars should be least of the following by this condition which is given in IS 446. The condition number 1 is the least lateral dimension of a compression member. In this column, the least lateral dimension is B. So 250 mm. The second condition is 16 times the smallest diameter of longitudinal reinforcement bar. Here we are using the single size diameter, that is 28. So 16 into 28, then we will get 448 mm or 300 mm. In these three values, we have to select the least value as a spacing or a pitch value for the lateral ties. Here the least value is 250. Therefore, we are providing 8 mm diameter lateral ties at 250 mm center to center throughout the column. Next we will see reinforcement details. This is a cross section of the column and this is a longitudinal section of the column. We got 8 number of 28 mm diameter bars as a longitudinal bars. So we will provide 28 mm diameter bars at all the corners of the column, and at the middle also we will provide one bar. Next is 8 mm dia lateral ties at 250 mm center to center, we got it. In cross section, this outer bar is called a lateral ties. In longitudinal section, the horizontal lines are called lateral ties and these vertical lines, outer bars, are called the main bars of 28 mm diameter. And these middle bars are supporting bars which are provided to hold the main bar. This is how we provide the reinforcement in a column. If you have any doubt, let me know in comment section.